just stick with it. Just pay attention, and if get these last 2 chapters under your belt, and you'll be good to go. All right, so chapter 10, really what we're talking about, and I used that word earlier, what we're talking about here is bivariate data. So you'll see that term in lab number 4, like again in the second part there that I posted this week, right? You can see that if you want to download that document. And take a look at that over the weekend. It's a good idea. I like it. I got some people posting some stuff on statistics. Very good. But up here on Tuesday, the second part of the lab. So that's the end, right? That'd be the last project that you guys have to do other than write the final exam. So again, this is just a continuation from part 1 of the assignment that we started working on last week. So you can take a look at that this weekend. But it's going to be using the concepts that we learned today. So bivariate data essentially just means that each sample contains 2 pieces of information. That's what the bivariate, 2 variables. And in the case of lab number 4, when you read that thing, what you'll see that we're trying to do is we're going to change the length of the pendulum and see how the effect is on the period of the pendulum. We're going to explore essentially we're going to say, how does the length of the pendulum relate? So that's the key word, correlation. How does the length of a pendulum relate to the period? In other words, the time it takes to make one oscillation, right? The period of a pendulum defined as, when you drop it, it swings and then it comes back. That's one period. And as we'll see, that the longer your pendulum, the slower the period. But we want to see if that's actually true, right? Unless you test it yourself, you don't really know, right? Again, that's kind of the basis of this course and of science in general is, the idea of not taking things for granted. Now, again, so you have 2 variables, right? There's the length and the period. And in this case, we're going to call, which one are we modifying? So when we're talking about variables, there's really 3 types of variables. Well, there's maybe actually 4 types. And this is, again, going back to chapter 1. There's 4 types of variables. Now, in this case, what we're going to call the independent variable is also known as it's the same thing as the manipulated. And on a graph, it's the same thing as the x variable. So when you graph this data, make sure you have the length on the x-axis. So the one you're going to change, right, when you read the protocol, what you're manipulating, right, you can't manipulate the period, you can manipulate the length. And so in this case, this would be the length of the pendulum. Whereas the other variables, is the one that's dependent, right? In other words, this is the one we measure. And that's going to be on the y-axis of your graph. and in this case would be the period or the time, right? Maybe I should just quickly define this, because I actually had a couple of students reach out to me and they're saying that from part one, when they calculate their acceleration due to gravity, it was a little weird. Like it was like, 13 or 14 meters per second. It should be closer to 10. But if you're getting something that's a little off, it's probably because you didn't measure your length properly. So maybe it's a good idea to just kind of review this. The length of a pendulum, and I mentioned this in the lab report, but I want to just remind you that it's very important to have a precise and accurate measurement here, right? This is defined as the distance from where you're holding it, right? So wherever your pivot point is, so where you're holding the pendulum, from, I guess you can call it a pivot point, right? The part that's fixed to the center of mass. Right? So, I mean, if you have a string and you just have a very small weight on the end, like let's say a quarter or something like that, or just a very small thing, it's hard to figure out where your center of mass is going to be. You want to have a relatively heavy thing that you've attached it to, right? When I did it, I attached like just a little piece of string onto a set of keys, and the keys are so much heavier than the piece of cord that for all intents and purposes, you can say that the cord doesn't weigh anything, right? So you want to have, the mass, you want it to be much heavier than your cord, right? Like if you have, let's say again, you have right, if this is your lightweight cord, right, just a piece of string, it's not going to weigh very much, right? Like let's say the mass of this thing is like 5 grams or something. The mass of your pendulum, like the quarters or something like that, like this something's going to weigh like 200 grams or something like that. And so you can basically assume that the center of mass is going to be here, the center of your actual mass. So again, you want this thing to be much heavier, right? You want the weight of your of the mass to be much greater than the weight of your cord. And then that way, when you measure the distance of your pendulum, you make sure you include that little bit into the mass, right? So if you have, you know, like the keys are this big, make sure you measure it to the middle there, or else your length is going to be off. And try and get it, relatively precise, right? If you just use something like, let's say you approximate it to 40 centimeters or whatever, but in reality, it's actually 37.2, you're going to get a much different answer, right? You want to be as accurate and precise with this measurement as possible. And every time you use it, make sure you're trying to get, try and get it exactly what it is. Okay, the period, right? That's defined as, right? You're going to measure that with your stopwatch, right? That is the time. Whoops. You're measuring it in terms of 5. I think in the protocol it says measure how long it takes for 5 to go, because that's just, it reduces human error, right? You can like set it and then you count 1, it reduces human error if you do it by 5, but the number you actually use, you're gonna have to divide that by 5, right? The period is the time for one oscillation. Right? So in other words, for it to come back to its original position. Okay, so that's what you're measuring. So you're going to graph those two things. But the third variable are things that are called controlled variables. Right? These are things that do not change. These are fixed. And examples would be, in this case, the mass. Right? You're not changing the mass of your pendulum. I don't know that you're not changing the density of the air, or the, you're not changing the temperature. Right? Things you're not changing that might influence the experiment. The mass should not influence the experiment, but the fourth type of variable, and we talked about this in chapter 1, is something called a confounding variable. And these are things you cannot control. Right? What's the equation again? The period 2 pi L over G. As you can see here, it's actually, if you just isolate the important ones here, or another way of saying it is you can say T squared varies with L, like that. So you have to do, as you'll see, although if you don't, you're going to get like an exponential thing here, but you're going to get a straight line. If you plot T squared, that's what they ask you to do. They show you to do that they tell you to do that in the procedure. So you're always going to have an X and a Y, and there's going to be a coordinate. And this is how you create a scatter plot. So in Excel, as we'll see in a little bit here, that's one type of graph that if you go back to chapter 2, they talk about types of graphs, and scatter plot is a type of graph. Again, even though the final exam really just has questions from chapters 4 onwards, you still have to know the stuff from chapters 1, 2, and 3, because we use these things all the time, right? So if there's a positive correlation, that means that the slope is positive. If there's a negative correlation, that means the slope is negative, right? When you do what's called a line of best fit, so you plot all your data, right? So you collect your data and then you plot it. You can create what's called a line of best fit, or a linear, that's what a linear regression line is. So you've probably heard of a linear correlation line, linear regression line is just a fancy word for line of best fit. That's what we used to call it back in high school. A linear correlation is the same thing as a line of best fit. So you're going to have to determine a slope, and you're going to have to determine an intercept. And that defines this thing here. Now, what you see here, this R value, is what's called now it has no relation actually to Pearson, which is kind of funny. It was another Pearson that figured this out, not the same as the textbook publisher, but this is called the Pearson correlation coefficient. So no relation to the author. It's kind of yeah, a bad pun. But yeah, there's no correlation to Pearson, the publisher, but this guy named Pearson figured out the Pearson correlation coefficient, and that's what's known as R. And it is a measure of the strength of the relationship. Or significance, let's say, since we use that word a lot in statistics. It's a measure of the strength or the significance between the two variables. And it's always going to be, so if you have a value of 0, that's no correlation. If you have something around 0.5, that's kind of considered anywhere from like 0.5 to like, let's say 8. You would call that maybe a weak correlation. And if it's, usually between like 9 and 1, that's the biggest you can have. It's a strong correlation. And they can be negative values as well, because a negative just means the slope is down. Just means a negative correlation. But when we say R values, we usually talk in absolute values. So, this would be a strong correlation. But again, this is kind of arbitrary. Right, so here you have something where it's just random, right? Randomness over here. So there's no correlation. Here you have a correlation. This would be like an elliptical or this would be like a parabolic relationship, right? Like projectile motion. This looks like a parabolic kind of relationship, but it's not linear. So we don't really cover those. I feel like everybody went to sleep. Okay, good. This is a very complicated equation that you'll see on your formula sheet. Right, this is a nasty one. So use Excel. Don't ever use this. Right, it's so messy. In the old days, you could use your TI-82 or your TI-83 calculators. Again, when all these lectures were given in person, you could just use your calculator, because especially these graphing calculators have easy ways to do it. But let's just use Excel. This just shows you how they do it. Right, this is what's called a difference of squares analysis. But we don't want to do that by hand, right? Look at it just shows you the complicated nature of it. But, use Excel for all of this. I think this is the only one you might have to do by hand when we do the hypothesis testing part of it. You'll have to do that one by hand, but for all of this stuff, just use Excel. It's so much easier. Like use Excel for this, and this. This one here, you still have to, I don't know if Excel has a function for it, but use your calculator for this one. But for the other ones, just use Excel. Obviously, it's so much easier. Like this. So let's just take a look at, so the first step in all of this, right? So they're trying to figure out here, is there a relationship between the size of somebody's shoe print? It's kind of hard to see that, isn't it? So all they're saying here is there a relationship between the size of somebody's shoe? Like if I just found somebody's shoe like a detective, could I tell you how tall the person is? Or can I predict how tall somebody is based on their shoe size? But as you all know, there's people that have big feet that aren't that tall, and there's people that are tall with smaller feet. But the question is in general, is there a correlation between people with big shoes and tall? And the first step you would always do is graph this. Okay, so they graph it right here. So they're saying the shoe print, again, this one's a little bit confusing, but if they say, the question is, can we predict height? As soon as you see predict, this means that it's the dependent variable, right? This is going to be on the y-axis. Can we predict, right? Prediction is the y variable in an equation, right? When you have, y equals something, that's a prediction. Can we predict height from shoe size? And from implies that it's the x variable or the independent variable. And in order to do this, the first thing is you always graph it. So again, here's their, they take everything and they graph it, right? So if 29.7 would be here, 29.7, and then right, because these people have the same shoe size, but they are different height. So that's that variable there. But you always want to graph it first to make sure that it's not parabolic, or to make sure it's not an elliptical or some other type of like this looks like it could be linear, right? You could, it looks like you could do something like that, right? It's possible. It doesn't look very strong, right? These kind of are messing stuff up here. So let's actually I'll show you how to do all that stuff just really quickly here, because I only got about 10 minutes left. So let me here's how you would solve this, right? On your final exam, it says, what is the value of R? And it's going to ask you, what is the equation? And it's going to ask you, is it significant? And all that kind of stuff. But the first step is to always graph it. Okay, so step one, graph it. In other words, generate a scatter plot. Right, so you can just put in your variables like shoe size, and then height. And you would just go ahead and put in your numbers. So then we have everything we need in order to get started here, right? So you would say, all right, I want to make a graph, right? Height as a function of shoe size. So in other words, y as a function of x. And then you can add your axes just like you've done before, right? Now here's the secret here. Here's what you want to do. What you want to do is you want to go to trend line. So that's the secret. The trend line allows you to put in the line of best fit. So you go trend line. Okay, select that. So that's going to be your y equals mx plus b right there. And then here's some fancy stuff to do here. Go, yeah, it's linear. Then go to more options. Okay, go to more options. Right, so we've got linear. Display equation on the chart. There you go, boom. Display equation. Beautiful. So that gives you your slope and all that stuff right there. Okay, so telling you the slope is 1.73. It tells you that the intercept is 125 5.41. So that's nice, but so that's cool. We have the equation. Now, how do we figure out the R value? Well, to figure out the R value, all you have to do here is say equals correlation, correl. And then here we'll get the R value. So 0.59. So that 0.59 is a weak value, right? I would call this is very weak at best. Now the question is this significant or not, right? Can we say that there actually is a correlation? Can we say that there is a weak correlation, or can we not? Now, in order to do that, we're gonna have to do the same thing we did in chapter 8, and it's the same thing we're gonna have to do in chapter 11 as well, is we're gonna have to do a hypothesis test. Just like everything from chapters 8, 10, and 11 require you to do a hypothesis test at this point to see if it is significant. Right? We have a weak relationship, but it might not be a significant relationship. Okay, so there we go. So they got the same number, right? Their R value, 0.59. I'll talk about R squared. I guess I can talk about it now. It just means that how much of the variation in Y, so R squared value is something that you just take R, it's just going to be your R squared. But it's going to give you the percent of change in Y that can be explained by X. So in this case, like 0.35, well, times 100. 35% is not a lot, right? So if you say that, okay, if we change the shoe size, and how much of the change in Y is due to that, and you say 35%, it's not a major factor. So in other words, right? So in other words, it doesn't look significant. And so what we're going to do is you're going to do a hypothesis test, right? So is this relationship significant? It doesn't look so. It looks weak. It's just a 35% correlation coefficient. So how do you actually figure this out? Well, you're going to say in this case, the null hypothesis in all of correlation is that there is no relationship. So just like R is this is going to be the sample correlation coefficient. We're going to use rho. It kind of looks like a P, but more of a on its side like that. This is going to be the population correlation coefficient. And so you're going to say that the null hypothesis for all of this is there's no relationship. Because again, we're taking kind of the null hypothesis is like the status quo or the skeptic's opinion, right? We're going to say that why would there be a relationship? Right? So again, it's kind of like the Occam's razor. The null hypothesis is like, all right, whatever we know from the background, and we don't know anything, so we're going to say the null hypothesis is there is no relationship. In other words, zero. And the alternative hypothesis for this is always that it's not zero, so that there is a significant relationship. Okay, I'm out of time today. For me to go into the rest of this is going to take too much entertaining as well. So you have to wait a while.